Hello guys, this is gonna be the video for laboratory number 12, which is gonna be chemical reactions and heat changes. A few of the goals in this for this laboratory, you will be performing two different reactions. The first one is gonna be between ammonium nitrate and water. The second one is gonna be a neutralization, as those you have seen so far, with between hydrochloric acid and sodium hydroxide. These are the different conditions you will need to consider further for these reactions to go on. So you will have the sets of data and you will just have to interpret the data and make the calculations corresponding for this. The final goal and the main idea for this whole laboratory is just gonna be to understand how are the heat changes you can have when you're performing a reaction. That could be either that you have an exothermic reaction, as this one I'm showing you here, or an endothermic reaction. For an exothermic reaction, you could think of an explosion, an explosive, like TNT, for instance. When you have TNT has very fast kinetics, and when you perform that reaction, you will liberate to the environment huge amounts of energy. So in that case, if this is the bomb and you are liberating in this case big amounts of energy to the environment, you will have an exothermic reaction which is going to result in heat getting released to the environment. On the other side, conversely, when you have an endothermic reaction, and you could think of it when you're cooking, for instance, if you're cooking rice, let's say, when you are cooking it, you need to employ energy for you to cook the actual rice, right? Well, that's an endothermic reaction because it needs external heat for it to get done, for it to get completed, the reaction. So those are the two different types of reactions you will be dealing in this laboratory, and we normally refer to the, mathematical and physical amounts that describes these endothermic and exothermic reactions as the enthalpy. The enthalpy is going to be always expressed with a capital H, and this is the delta. So it's always is going to be a change in the enthalpy. Okay. We can relate this change in enthalpy with the change in heat, or how, so this is a way for us to measure how much heat is getting released to the environment, or how much energy is getting applied to your system in terms of heat. Okay? Moving forward, a few considerations before we go on with this laboratory. So this is going to be a 2 week lab experience, which means that you will have 2 weeks to complete this, which is going to be your final report. So keep that in mind as well. So please take your time in this case and try to attempt a good score. So this is the last one. It's just the last one, at least regarding to the lab sessions. So please keep that in mind and make an extra effort for this one so you can get a good score, guys. I encourage you to try it. Okay, for this laboratory, significant figures matters, so please take that to consideration when you are reporting your results, because we were instructed for this lab to be very careful about the significant figures, and I will be grading. And even though if you get a good number, or the appropriate result, if you don't express that result to me with the appropriate amount of significant figures, I will have to withdraw your points, and I don't want to do that. So please keep that in consideration. And as I told you guys, this is the lab session. So congrats, you're about to finish the laboratory. So please, one extra effort for this one last effort, and we should be done. Okay? About the absences and how are we going to account the absences after the spring break and the starting of this COVID-19 situation. Well, absence will be considered when you didn't submit your lab report. So if you didn't submit a lab report, you should know already beforehand that that's going to be considered as an absence. So please start doing your math as well. Count how many absences did you have throughout the semester, and if you have any concern about that, please let me know. Moving forward, the general information for this laboratory, the temperature probe, in this case is the way you can actually make these calculations. So it's very simple. We will be using for this a calorimeter. Calorimeter is simply in this case this very rustic system you have over here, where you have two, coffee cups made of foam, because foam is, is very good insulating heat, so that's the reason why we use that material. You have to stir constantly your solution so you can perform your reaction. So this red pellet over here is standing as a stir bar, and then you're measuring your temperature at all times. So you could use, imagine that you have certain amount of water in here, and once you add your ammonium nitrate, let's say, you will start a chemical reaction. Well then, once you start your chemical reaction, you will notice a change in the temperature because you have the probe probing at all times the temperature of your system. And that change in temperature is gonna enable you to measure the heat change between the heat exchange, sorry, between the surroundings, which is everything but your, you know, cup of coffee with the reaction going on, and your system, which is gonna be the actual cup of coffee with the probe and so on. Okay, so this is the basic setup you would have done in the laboratory, and that's basically it. Moving forward, these are the basic calculations you should be performing for this laboratory. So you will be measuring the amount of heat of the surroundings and the amount of heat of your system. You need to know that the heat of the system and the heat of the surroundings are completely antagonistic, which means that if your system is winning energy, the surroundings needs to be losing that energy, because remember that the energy cannot be destroyed or created, right? Because of thermodynamics. Well, these are thermodynamics. So if you are losing energy from your system or you are winning it, that means that your surroundings need to be winning it or losing it, depending on the circumstances. Okay, keep that in mind. Coming back to this equation here, the K of the surroundings, or the heat of the surroundings, it's gonna be equal to the mass of your solution in grams times your delta T, which is gonna be the change in temperature. Remember that you were measuring the temperature before you started the reaction and after you finish the reaction. So you need those two temperatures to make your delta T, which is gonna be equal to the final temperature minus the initial temperature, and that's gonna be times C, which in this case is gonna be the specific heat capacity. Speaking of, so what is heat capacity and why is it important? Well, if we take a look at the formula, we have that heat equals mass times the specific heat times the change in temperature, or delta T. And if we go specifically to the specific heat and what units it has, you can see that it has units of joules, which is expressing nothing but energy per gram times degrees Celsius. So how can we interpret this information? Well, that is telling you that that's the amount of energy that you need in order for you to increase per 1 degree Celsius 1 gram of any kind of a specific solution or compound. And that's the reason why it is called specific, because this is related, completely related to the type of compound or solution or any type of reaction you're dealing with. Okay? So now moving forward to a specific example so you guys can understand how this is important, soils and soils health can be related to the specific capacity they have. If you have a soil with a big amount of water, that soil, it's supposed to be healthy, right? In this case, they are showing you here what should be a relatively healthy soil, whereas in this case, in the lower part of the diagram, they are showing you a very eroded and very dry soil. So how can we understand this? Well, if this soil has bigger amounts of water, and you can tell that out of, logic and common sense, that means that if you would want to take off that water from that soil by vaporizing it, you will need to apply heat, and you will need to apply bigger amount of heat in here than in here, because in here you have more water, because this soil has more water absorbed, whereas in this case for the absorbed, sorry, whereas in this case for the dry soil you can see underneath, you will need least amount of energy to take off the few water you could have within. So therefore, the specific heat capacity for this soil would be higher than the specific heat capacity for this soil over here. So the specific heat capacity of soils tells us right away about the health and the condition that soil is in. So I just wanted to point out this situation so you guys can understand what's the importance of this physical measurement in science in general. So, coming back to the presentation, you got to consider that for this laboratory, the signs that you use for for expressing the energy you either win or lose, it's gonna matter. It's gonna matter big time, and you need to consider that each time you are expressing data or you are performing any kind of calculation. For delta T, it's quite obvious, right? If your energy is getting increased, that means that the sign in the end is going to be positive. However, if you are losing temperature, if you started with, let's say, 25 degrees Celsius and then you went down to 15, well, you know that in the end, your change in temperature or your delta T, it's going to have a negative sign. And that matters for this calculation. So keep that in mind. Regarding the winning or losing of energy for the surroundings, well, the same in this case. If the temperature probe, which is going to be part of the surroundings, is gaining energy, that means that in the end, your K is going to have a positive sign. Conversely, if you are losing energy or your temperature probe is telling you that you are passing from in this case, from a higher temperature to a lower temperature, that is also going to affect the K surroundings by giving you in the end a negative sign. Now, speaking of the most important part in this case is the K of the system and the change of the enthalpy of your system. If your reaction, if your system, which is what you care about in this case, it's gaining energy upon the reaction, that means that you have an endothermic reaction. And you can think of it once again as if you were cooking. If you're cooking, you are performing an endothermic reaction because remember that you need to apply energy to cook rice, for instance, right? Well, then, if you need to apply energy to any kind of reaction in order for it to start and to go actually on, to carry on, that means that you have an endothermic reaction. Conversely, if we are looking at the reaction system and the system is losing energy upon the reaction, that means that we have an exothermic reaction, which means that the system is losing energy and therefore the surroundings are winning that energy that is getting, freed by the system. You can think of it as an explosive. For instance, TNT. Once you perform a reaction, a specific reaction between TNT and moisture in the environment, let's say, for instance, that will represent a big liberation of that energy to the environment in a very violent and quick way, which is the reason why you have an explosion. Okay? I hope this helps. In the next video, I will be explaining all the calculations you need to perform with the recitation guide. So I will be going step by step in that recitation guide. So if you have any questions on how to make the calculations, I encourage you to go and watch that video. See you guys.